Okay, so let's make a start. So just in case you're not wondering what you're looking at, these are some additional lecture notes, and you keep in mind that everything that we're going to do for the next 2 days are non-examinable, so you're not going to see any of this in your exam to an extent, but at the same time you're going to learn something which actually provides you a little bit wider background than the things we've studied already. So the purpose of this short notes are really to talk about notions associated to conditional expectations and conditional probability density functions, some of which we've seen in our lecture notes. As you can see, there are 11 pages. We have 2 days, so 6 of the pages today, 5 of the pages tomorrow. So we finish when we finish. So this first block of notes, you should cast your minds back to the notion where we are looking at jointly defined random variables x and y, which are discrete. Okay, so the idea is, so there's only 5 of you here, or 10 of you here, so we can write the board. So I have a pair of random variables x and y, and that belongs in some set. Let's say the integers times the integers, or something like that. So basically, these random variables x and y are countably infinite. They could be, let's just say they're integer valued. Okay, so there's discrete pairs of random variables. Okay, so remember that capital F of xy, little f of xy, was the probability mass function representing the probability the random variable takes the value little x, and the random variable y taking the value little y simultaneously. Okay, now what we're going to study very interestingly, I think, in this part of this extra notes is the notion of conditional probability mass functions of y given x. Okay, so the idea, you can see in front of you, but the idea is that we want to study the conditional probability mass function of y given x. Okay, that's y given x. Okay, which we know is equal to the joint probability mass function of x and y. X and y. Okay, xy over the marginal f x of x. Okay, so that's the thing that we're going to study. Okay, a little bit of. Okay, so we recall that basically this thing is only well defined, this conditional probability mass function, the probability that y takes the value little y given x takes the value little x, if the probability of x is strictly positive. Okay, so we remark that basically we can rewrite this is the CDF, neither here nor there. So the conditional probability mass function, as I've written down, so I've in my notes here I get rid of the subscripts x and y, so I just write f of x, y, and this thing represents the joint probability mass function of x and y. Here I'm supposing x and y are just going to be having a particular type of structure. Sorry, I want to talk about this one. So this is the joint over the marginal on x, and remember that by definition the marginal on x and y are discrete. So f of x, fx of x is just the sum over all possible y's of fxy of xy. Okay, so this gives us a formula for computing conditional probability mass functions. Okay. Let's have a look at an example of trying to look at this. So here I take an example. So this notation is probably not very familiar to you because it's different to what you've seen before. But what this says is that y, a random variable y, is defined as being Poisson distributed, and x given y is binomially distributed. Okay, and actually this was a little bit in your last semester. So if you look at 2018 semester 1 exam, you will see something about this actually. So it's probably interesting to look at. So here you have x given y is binomial. Okay, binomial, and the parameters are little y, and the success probability is p, and we're saying y is distributed Poisson with parameter lambda. Okay, that means the probability that y takes the value little y is lambda to the y e to the minus lambda over y factorial. Okay, very good. Now we can compute the conditional mass function of y given x. So remember, in this situation, the support of these pairs of random variables, well, y is Poisson, so it can be any number from 0, 1 off to infinity, and x in this case is binomial, but it's binomial given y, so it has support only up to the value y. So basically now you can compute the conditional probability mass function of y given x, because that's the joint probability mass function over the marginal in x. Okay. Now we can use a basic quick derivation, so we know, so in this calculation here, what we have done is the fact that f of x, so f of xy is equal to f of x given y times f of y for any y for which f of y is positive. Okay, this is a simple calculation, and if you substitute in this numerator here for precisely that thing, you get this expression. Okay, and what's the significance of this expression? Well, the significance of the expression is that this is a version of Bayes' theorem when you use random variables. Okay, so remember we did Bayes' theorem before, and we were using events, but there's a Bayes' theorem for random variables. It just looks like that. Okay, now if you actually want to compute this conditional probability mass function of y given x, you need to find the marginal probability mass function of x, and this is contained in this calculation here. So I can very easily go through here. So what am I trying to do? I want to find this density function. I have this information here. This is the support of my random variables, and I'm going to use, in order to compute this, I need the denominator f of x, which is the marginal probability mass function of x. Okay, so we can do this calculation. It's fairly straightforward. Okay, you can see that they're all in front of you, the calculations, and we can study them. And like I say, this is not completely, whilst I'm not going to examine these notes, this example is not irrelevant for what we've studied, because like I say, this calculation was in last year's exam. I know that because last semester's exam. I know that because I was looking at it today. So the marginal probability mass functions, I'm just going to write this calculation. You don't have to copy anything. I'm just going to explain what is going on. So the marginal probability mass function fx of x, so x is now in the set 0, 1 off to infinity for any fixed x, okay, is equal to the sum over all y's of the joint. Well, y, so in this case, remember that you're saying that y must be at least the value of x. So the range of the summation, when I sum the joint probability mass function over all y's, it must start from x because of this constraint here. So this is the sum. Y is equal to from x to infinity. Okay, and then the joint probability mass function, which is this Poisson y choose x times p to the x times 1 minus p to the y minus x times the Poisson, which is lambda to the y eta minus lambda over y factorial. Okay, and then basically to kind of compute this is not so difficult, because basically you have this binomial coefficient y choose x, you have the term y factorial, so you can cancel some things and you can take out factors which are independent of y, so that's equal to what? So as I say, I take lambda times p to the power, lambda times p, what is that, lambda to p, p to the x? So minus lambda p to the x. Why is it p to the 1 minus p? Looks like a mistake to me. P to the x comes outside. Yeah, the result is right. Minus p. Oh, okay. 1 minus p. Yes, okay. So there is, what I've done here is I put the lambda inside here, and then I get an extra lambda here. Sorry. So this is lambda p to the power x. the sum y is equal x to infinity, x to infinity. Okay, so then I cancel for the binomial coefficients, so I'm basically going to get 1 over y minus x factorial, and this x factorial is going to come outside. I get e to the minus lambda comes outside, and I get this 1 minus p times lambda to the power y minus x. Okay, so just to say that this extra lambda comes from the fact that I put the lambda here, so I get an extra lambda to the power y minus x, so I must get lambda to the x here. Okay, and now this summation, how do you do it? Well, you just change the summation limits. You set u is equal to y minus x, so the summation basically becomes so the summation by itself is this summation here is just the same as the sum. Let's say u equals 0 to infinity of 1 over u factorial times 1 minus p lambda to the power u, okay, which is just equal to e to the power 1 minus p times lambda. Okay, so then what you do is you have a lambda p to the x over x factorial, and I have e to the minus lambda, but I have e to the 1 minus p times lambda, which gives me e to the minus lambda p. Okay, and what that means is that the marginal probability mass function of x is exactly Poisson lambda p. Okay, so then what that means is now we can compute the conditional probability mass function of y. Yes? Because, as I said, this thing is only defined if x is less than or equal to y, so y must be at least the value of x, otherwise this thing is 0. Okay, so this comes from the support. Okay, so the conditional probability mass function of y given x is precisely then the numerator of this equation is just the product of the mass function induced by this one and the mass function induced by this one divided by this factor here. And if you do a little bit of algebra, which we don't do, but just to save ourselves some work, this is basically a conditional Poisson distribution. So it says that y must be at least x plus 1 as specified, and this is basically like a type of Poisson. Okay. So given the notion of conditional probability mass functions, one also has the notion of conditional expectations. So the conditional expectation is one expects, basically the conditional expectation of y given x is the sum over the support of the y's of y times the conditional probability mass function of y given x. Of course, given that the conditional probability mass function is well defined at the point little x. Okay? And we really, normally what we write is the expected value of y given x if x is random, or the expected value of y given little x if x is constant. Okay. Right. Okay. So that's the notion of conditional expectation, and this is actually a special or important notion here, because this formula, which is kind of fundamental in probability, it's amazing that we have not been, I don't think we even taught you this, that if you want to compute the expectation of y, that's the same as if you have two jointly defined random variables, x and y, the expectation of y is the same as computing the conditional expectation of y given x and then averaging over y's. It's called it's kind of a type of tower property. It's very straightforward to establish, so I will show you how to do that. So the idea is that we will start here on the right-hand side and we will derive the left-hand side. So by definition, the expectation of y is equal to the sum over all possible y's of y times f of y. Okay, that's what it is by definition. Okay, now I can expand the space that I'm summing over, because I can sum over all x and y's of y times f of x, y. Because by definition, remember that basically what we're doing here is that f of y is the sum over all x's of f of x, y. So this we're just making the substitution that the marginal, this marginal is just equal to the joint summed over all x's. That's all you do there. Okay, and now that's it really, because now we know the trick that we showed you earlier, that the joint fxy is the conditional y given x times f of x. Okay, there's nothing complicated to go to the next line. Alright, and then what we do, well, basically now I've got a double sum. I can sum first with respect to x and then y, or y then x. It doesn't make a difference for us in this case. And so basically this, if I sum first with respect to y, this thing is by definition the conditional expectation of y given x. Okay, and moreover it's a function of x, so this is a function of x, so the expectation of a function of x, and the function of x here happens to be the conditional expectation. Okay, and so it basically provides you a nice formula for computing expectations when I, for example, have access to the conditional structure of y given x, but I don't have access to the marginal structure of y. So if you remember in our example, we just go back to that. If you have y is Poisson, x given y is binomial, so that's the example we were just wanting to look at. Let's have a look at computing the expected value of x given y, y given x, and the expectation of x. Okay, so this is fairly straightforward for a couple of these things, giving you a result. So remember that if you have z is binomially distributed, so this b means binomial, with parameters np, then the expectation of z is n times p. Okay, so basically, first of all, the expected value of x given y is straightforward, because x given y is binomial yp, so the expectation of this random variable x given y is basically going to equal y times p. Okay, that's straightforward. Now if I want to find the expectation of x, okay, in this information I'm not given the marginal distribution of x. Of course we have calculated it, I think, up here, so we know what it is, but if we didn't want to do this computation, it turns out that computing the expectation of x is really straightforward using our formula here with the roles of x and y interchange. So the expectation of x is equal to, by using that theorem 1.1, the expectation of x given y, and then I average over the uncertainty in y. But I know the expectation of x given y is y times p. P is a constant, so the expectation of x is equal to p times the expectation of y. Okay. And now I'm in a good position because I know y is Poisson lambda, so the distribution, so if y is Poisson lambda, the expectation of a Poisson distribution with parameter lambda is lambda. So therefore the expectation of x is just p times lambda. Okay, so now what we have done is we've computed the expectation of x given y and the expectation of x, and we're now left with computing the expectation of y given x. Okay, well, we've already computed the conditional probability mass function of y given x. That was the result of the calculation that we just did a few moments ago, and so now what we're going to do is to basically use the definition to compute the expectation. Okay, so by definition, the conditional expectation of y given x is y times the sum over all possible values of y, so y goes x plus 1, so this is x to infinity, and this is the conditional probability mass function. Okay, so now what we're going to do is we're going to pull the same trick that we did a few moments ago. So we're going to change the limits of summation. Instead of going from x to infinity, I'm going to go from 0 to infinity. The reason why I want to do that is basically the associated computation is going to be easier. So I set u is equal y minus x. So now u goes from 0 to infinity instead of from x to infinity. Y, well, that's equal to u plus x. Y is equal to u plus x from here. Okay, then I have lambda 1 minus p to the power y minus x. Y minus x is u. E to the minus lambda 1 minus p is a constant, and u is equal to y minus x, so I get u factorial. Okay, very good. So now what do I do? So the key point to realize at this point is that this factor here is the mass function of a Poisson distribution with parameter lambda times 1 minus p. Okay, so what does that mean? Well, in this equation, x is a constant, so the expectation of a constant is a constant. So the expectation of u plus x is the expectation of u plus the expectation of the constant x, which is x. Okay, so that's where you get the x from here. And now this is just the expectation of a Poisson random variable with parameter lambda 1 minus p, which we have already worked out is lambda times 1 minus p. So this is the conditional expectation of y given x. Okay, and this is what I'm saying here. U is Poisson lambda 1 minus p. Is just the fact that this is the mass function for Poisson with parameter lambda 1 minus p. Okay, so the key point is that you can calculate all these things relatively straightforwardly. Okay, so we'll just finish one. Well, I don't know if we'll ever use this result in this course, or this small course, mini course, I guess. You also have an additional result that if you want to compute the expected value of y times g of x, so that here you were interested in the right hand side, what I can do first is compute the expected value of y given x and then multiply that by g and then average this over g. Okay, over x, excuse me. This is what this result says. If I want the right hand side, I can compute the conditional expectation of y given x first and then average over the uncertainty in x by multiplying then by g. Okay, so let's do this. This is not very easy, not very difficult to justify. So as before, we start with the right hand side, which is what we're really interested in, and then we would derive the left hand side. So by definition, the expectation of a pair of random variables, a function of random variables x and y, is just the sum over all possible x and y's of y times g of x times the joint property mass function. There's nothing too complicated here. Okay, so now what can you do? Well, we use the same trick as before. F of x y is equal to the conditional of y given x times f of x. Again, nothing too complicated now. And then what do? Well, I sum over y first and then x. And if I sum over y first, basically in this bracket here, the only expressions which depend on y are y times f of y given x. And this thing by definition is the conditional expectation of y given x. So this gives you the result that one wanted to prove. And it's completely useful in other contexts, some context, which we will see. I mean, the key point, and the point of why am I telling you all these things, is just to show you that the lecture notes that we've explored only touch upon a small part of probability and statistics, and that if in fact one ever wants to be doing probability and statistics properly, that these are the kind of things that one has to be able to do. This is the thing you would teach a math major in year 1. Okay, but you're not math majors, so it's not as important for you. Okay, so what we're going to do well, I guess there's not that much left for today, but anyway, there's still, well, we are halfway through. We're going to study now the notion of conditional expectations, whether a pair of random variables x and y are continuous. Now, the key point is, as if you remember, we were just talking about it, that if you want to consider the probability mass function for y given x, that essentially, in order to do that, one must condition on events of non-zero probability. So if you remember going back all the way to when we studied probabilities of events, the probability of A given B is the probability of A and B over the probability of B, provided the probability of B is positive. Okay, and similarly here, this is a similar thing. Here's the probability x is equal to x is positive. So what we want to do now is to study this notion, but the random variables x and y are continuous. Okay, and the key point is now, how do I construct a conditional density function of y given x if x and y are now continuous, if we know a priori the probability that event x equals x is 0? That is what we have learned from the beginning, if you remember. This is what this whole information turns out to be. Well, the whole point, the whole issue, indeed the event x equals x is empty, is a null set, I has probability 0, and the basic point is, in order to define a conditional expectation in this particular framework, one must actually start more fundamentally from a different mathematical perspective. So even for math majors, we do not teach them what a conditional expectation is, and so essentially you're going to have to take what I say at face value, because the way to construct a definition of an expectation, conditional expectation, it is based upon a level of mathematics which is not even taught for math majors. So you're going to have to believe what I say here. So if you want to find the conditional density function, or distribution function in this case, of y given x, is defined to be y and x are real valued here. So the integral between minus infinity to y of the joint f of x here v, because I'm going to integrate over v, over the marginal f(x), okay, for any dense point in the space where the density function is strictly positive. So mention that here, this does not, of course, if f of x is positive, it doesn't mean that the probability of x is bigger than 0, it just means its density is positive, okay. So this is how we define conditional probability density functions, even though we know that we're conditioning on events with 0 probability. And the conditional density function is exactly like we'd written down for the probability mass function case. You take the joint density function of x and y, and you divide, in this case, by the marginal probability mass density function of x, where we're assuming that x is any point such that the density is positive. Okay, and clearly one can write this as this expression, because in the denominator, f of x by definition is the marginal, so I take the joint probability density function of x and y and I integrate over all possible values of y. Okay, so here if y is real value, it's between minus infinity to infinity. Okay, so let's have a look at some examples. This one is a bit tedious, but never mind. So here in this example, what we say is the following. So this is an example where we define a density function y given x is Gaussian with mean little x and variance 1, and x marginally is normal 0, 1. Okay, so the support of this random variable, so I'm using this sans serif z for the support, is just the product space r times r. Okay, and what we're going to do, we're going to find the conditional PDF of x given y and the joint PDF of x and y. Okay, so f of xy is straightforward, because f of xy is equal to the conditional y given x, which I know, times the marginal f of x, which I know. I know that this one is Gaussian and that this one is Gaussian. So basically the joint PDF of x and y, well, I just do this thing here, this part comes from the conditional y given x, this comes from the condition the marginal on x. I get 1 over 2 pi, because basically I get 1 over root 2 pi squared, which is 1 over 2 pi. Okay, so the joint PDF here is straightforward. No one does not have to do anything too complicated. Now, in order to find the conditional density of x given y, well, we then apply this formula. This is x given y is the joint f of x y over f of y. Okay, we just interchange the roles of x and y from up here. Okay, so this is y given x, this is x given y. It's the same thing, I'm just changing the roles. Okay, and now this joint density, well, I know the joint density f of xy, okay, but we use the formula that this thing is equal to f of y given x. This is what we wrote here. And the formula that's written here, okay, is what? Well, it's called Bayes, and again, it's a Bayes theorem, and it's a Bayes theorem for continuous random variables. I think the roles of x and y are interchanged from what we said before. Okay, this is what they say. So in order now to find the conditional density function of x given y, I have y given x, I have f of x. So, well, it turns out you don't need the denominator, but we're going to calculate it anyway. So now to find the conditional density function, these are just computations, so I'll take you through them relatively painlessly. So the density function at f of y is by definition, this is the joint PDF of x and y. Okay, that's what I've written up here. Okay, and all I need to do is to integrate over all x's for fixed y in the support. So here we fix y in the reals, and now I just integrate this function with respect to x. Okay, and basically the way to do this type of integrals, if you're ever interested in doing these things, is I want to turn this into a function. Let me just write down this thing. So what I want to do is I want to turn the integral. So I want to turn the integral to look like something like minus infinity to infinity of exponential of minus beta x minus alpha square dx. I mean, this is what we're trying to do. Why am I trying to do that? Because I know what that integral is. Because this is Gaussian type integrals, and I can use the formula to do that. Instead of doing a double integral, I can do a single. I don't have to do anything. So that's the only trick here. Okay, that's all I'm trying to do. Alpha and beta in my formula are constants. Okay, I've got myself tangled up, sorry. Okay, so basically that's all I'm doing. So this line is just from the definition of marginal probability density functions. Okay, and see I've got the joint here. So what do I do? So I just multiply out the brackets. This is y minus x all squared, so it's y squared plus x squared minus 2xy. Okay, I have x squared here. So the formula, so of course y squared is a constant in the integral, so I can take it out. Okay, so 1 over 2 pi. So this is just taking out what that's known. And now I have inside the integral exponential minus 1 over 2, 2x squared minus 2xy. Okay, so now I just complete the square, so I can say that this term here is precisely equal to this time here, okay, when I'm multiplying by 1 upon 2. So you take the 1 upon 2 out and you complete the square. So if I multiply this out, this is x squared plus y squared over 4 minus xy, okay. So the y squared over 4, you'll lose the quadratic here, and you'll go back, so we're going to get minus 2x squared minus 2xy over 2. Okay, this is all you've done here. Okay, so the nice thing here now, e to the minus y squared over 4, I can take it out here, so I get e to the minus y squared over 4. Okay, and now I have this integral. So this integral here, when I have this thing, I can then just use a change of variable. I make the change of variable u is equal to x minus y over 2. And so then I get e to the minus u squared over 2, and I get 1 over root 2 from the Jacobian. Okay. And now this integral I know because I know the integral between minus infinity to infinity of e to the minus u squared over 2 du is root 2 pi. Okay. That's a formula which, in fact, we quoted in the main lecture notes. So this is where this root 2 pi comes from. The 1 over root 2 is here. I have a 2 pi here, and e to the minus y squared over 4. So just some simple calculation will give you that this is the marginal PDF of y. So in fact, what this is the PDF of a normal distribution with 0 mean and variance 2. That's what this thing means here. So basically, to summarize, the conditional density function of x given y, with this numerator I've got it, it's up here. This denominator we've just calculated. So the conditional density function of x given y looks like this. And if you do a bit of algebra, which obviously I'm saving me doing, it turns out to look like this. Okay, and that's basically a Gaussian distribution with mean little y over 2 and variance 1 over 2. Okay, so just an example. Okay, so another example. This one is a little bit involved. But, again, like I say, these examples are not examined, so you don't have to be able to do anything this hard in the exam. So with two examples now. So here I define two random variables x and y, they're continuous. The joint PDF f of xy is 1 over x, where x and y belong to this set. So x and y is such that y is less than x is less than 1, and y is bigger than 0. Okay, so this is defining the support, and you can check that this thing integrates to 1 because fx of x, for example, okay, so I fix x in 0, 1, and I integrate over y, so y goes between 0 and x, so I go 0 and x, the PDF is 1 over x, and I integrate with respect to y. So this thing is equal to 1, okay, so the marginal density function of fx of x is uniform on 0, 1, okay, so of course if I now integrate the function 1 between 0 and 1, I get back 1. Okay, so that's the marginal of x, the conditional density of y given x. So if I take x and y in this set, so f of x, y given x is the joint 1 over x over the marginal on x, which is 1. So this is, so y given x is what? That is to say, if x is in 0, 1, then conditional upon x, y is uniform naught x. Okay, so this is uniform naught x distribution. Okay, so those are some things there. So now what we're going to do is we're going to compute, you may be interested in this, you're not, but the probability x squared plus y squared is less than 1. This is all to do with circles. So I'm going to compute this probability given I know x is equal to x, and we let x be positive. So for some positive x, we define the set A of x, which is the collection of y's such that y is in this, basically in our support, and x squared plus y square is less than or equal to 1. So that is to say a of x is this interval between 0 and the minimum of x and x 1 minus x squared times 1 over 2. Okay, this is what it is. This sign a wedge b means the minimum of a and b. Okay, So basically what we want to do is we want to compute the probability that x squared plus y squared is equal to 1 given I know x is the integral of the conditional density of y given x over this set. Okay, so the conditional density of y given x, we know it's 1 upon x, and a of x is the integral between 0 and the minimum of x and 1 minus x squared over square root. You get this one, it comes from here. Okay. Okay, so this is a simple integral, you don't have to do anything. Okay, this is just equal to the minimum of x and 1 minus x squared over square root over x. This is a probability, you can check it. Okay, because if you get x over x, which is 1. Okay, and if it's this one is less than this, so this is less than 1. Okay, now if you are interested in computing the probability now that x squared plus y squared is less than or equal to 1, you can do that very simply. Okay, so we now denote the set x and y such that x and y belongs to this set z, where this is a support of the random variable, and x squared plus y squared is less than or equal to 1. So I want to compute the probability of a. That's what you want to do. Okay, so the probability of a is the probability density function of x and y integrated over all possible over a. That's what it is by definition. Okay, so that's equal to what? Well, that's the conditional probability. So this here is the conditional probability that x squared plus y squared is less than or equal to 1 given I know the value of x, and then I integrate over all possible values of x. Okay, now this thing here that I've highlighted, we've done it already. It's just equal to this number. Okay, so now all I want to do is I want to compute this integral. Okay, so there's a marginal type here. This should be x, not x squared. So if x is less than or equal to 1 minus x squared over square rooted, then it means x must be less than or equal to 1 over square root of 2. It's a simple inequality to solve. So this probability is equal to, so if x is less than or equal to 1 over root 2, then basically I'm going to get 1 here. So I get the integral with 0, 1 over root 2 dx, and otherwise I'm going to get this thing. Okay, so this one obviously there's no problem. This is a difficult integral to solve, and which is not a course in integration. I'm just telling you some things. In order to compute this integral, you can do this trigonometric substitution. X is equal cos theta, and if you do that, it's a simple change of variable formula. You get this. Okay. Now doing this integral is non-trivial, so you can have a look at a table. This is what I did when I got this integral, and the table tells you that this integral is equal to this. You can check by differentiating. And so basically the conclusion is that this integral here is log of 1 plus root 2 minus 1 over root 2. Okay, so the probability of interest is 1 over root 2 plus this, so I'm getting log of 1 plus root 2. Okay. All right, very good. So we're almost finished. I'm just going to do one more page. So that was just an example. So given the previous discussion, so we know how to look at conditional PDFs to some extent. You can also look at conditional expectations. So basically, essentially, we define the conditional expectation for jointly continuous random variables of a functional g of y given x is just the functional g times the conditional PDF of y given x, integrated over all possible values of y. And basically, we can get an analog of the formula that we had before. So if you remember this formula here, right, this is the expectation of y given x, g of x is equal to the expectation of y gx. You can get something analogous in the continuous case. Because if I want the expectation of h times g, that's the same as computing the conditional expectation of g given y x first, and then multiplying by h and then integrating out. Okay? You can verify that formula. It's very, very simple to do that. But the key point is, if I want this, I can compute this first, and it may be easier to do my associated computation. Let's have a look at an example. This is very short. We're going to stop here, by the way, so we're almost finished. So let's have a look. So suppose that y given x is normal x1 and x is normal 0,1. Okay. And if I suppose I want to compute the expectation of x times y, right? Why is that important? You might want to compute the correlation between x and y. Okay, well this formula says what I can do is I can compute the conditional expectation of x given y first, multiply that by y, and then average over the uncertainty. So the expectation of x given y, I know it because basically x given y, so here it's from this formula here, so x given y, it's up here. Where did we get it? X given y was normal y over 2, 1 upon 2. So this is expected value of x given y is y over 2. Okay, so then I take this 1 upon 2 and I want to compute the expectation of y squared. Okay, but we know the marginal density of y because y is normal 0, 2. So the expected value of y squared is 2. Okay, so this is why you get 2 over 2, which is 1. So basically that gives you the covariance. So basically this is the covariance because the correlation is the expected value of x, y minus the expected value of x, which is 0, so I don't care what the expected value of y is, divided by the square roots of the variance. So the variance of x is 1, the variance of y is 2, so the correlation is 1 over square root of 2. Right? And the key point, why is that interesting? Well, the thing is that this is a kind of more painless thing to do than to do this from the definition. Okay. Okay, and this is just one remark. One final way or final use of these conditional expectations. Okay, so we're almost finished. So I say y given x, that's normal with mean x and variance sigma squared, and x is normal xi sigma squared 2. Okay, now if you want to find the marginal of y, of course you can multiply the density function of this by the density function of this, and then integrate over all possible x's, but it's less painful if you use moment generating functions, which I've told you about very briefly before. So let me just show you why these calculations are useful. So if I want to find the moment generating function of y, it's by definition the expected value of e to the yt. Now I can apply my formula, so I just compute the expectation of this random variable conditional on x. Okay, but I know the conditional distribution of y given x is Gaussian with mean x and variance sigma square 1. The moment generating function of such a thing is just going to be e to the xt plus 1 upon 2 sigma squared 1 squared over 2. Okay, this is just a moment generating function for a Gaussian. Okay, so I can take out the constant e to the sigma square 1 over t squared over 2, and I got the expectation of xt. This thing now, x is normal xi sigma squared 2, so this thing is equal to e to the xi t plus sigma squared 2 over t squared over 2. Okay, and if you put the formula together, this is what you get at the end. What does it mean? Well, it means that the marginal distribution of y is normal with mean xi and the sum of the two variances. And that's it. And basically, we've just used some results on conditional expectations. All right, let me just finish up. This is a painless slide, so this is a painless comment. So just to finish off these additional notes, what we're going to look at tomorrow is the notion of Bayesian statistical inference. So the idea is that what we have looked at in the main lecture notes, the thing that we have studied a little bit, is maximum likelihood estimation. So I have a random sample of data, a random sample which represents a population. I realize that information, and that gives me basically the likelihood function of the data, and I try to maximize that function with respect to the unknown parameter. Now this is basically a different way to do statistical inference, where you assume that the parameter that you want to estimate is a random variable. So in the previous two sections, we've looked at these conditional PMFs and PDFs. So this is a formula we derived twice in today's lecture. Okay, and basically you can use this representation to kind of formulate a kind of school of statistical thought. Okay, this is a very well-known thing that people use this all over the place. So let's have a look. So this is just this slide, and I'll finish here. So basically, we assume we have a random sample, so a collection of IID random variables, which are conditionally independent. That is to say, if you give me a parameter theta, then they're basically independent. Okay. So basically, theta is going to be a random variable. So we assume that xi is given theta, or IID, with some distribution function. So that's to say that the joint density function of all these random variables, it looks like this. It should look very familiar because this is what we did when doing maximum likelihood estimation. So the statistical paradigm which we're proposing in this context is that basically now the thing that I'm interested in, remember I want to estimate the mean of the data, I want to estimate the variance, the population parameters. Okay, the way in which this framework proceeds is by placing a probability distribution over the unknown parameter theta and trying to infer that the value of that parameter conditional on the data, basically using Bayes' theorem. Okay. And so, for example, if the xi, suppose we have the random sample which are exponentially distributed, so here's theta's lambda, then basically you have to construct a probability distribution over theta which is positive. So, for example, you can use the gamma distribution which is related to the F distribution, we saw it before. And you can specify those parameters A and B if you know something about lambda before you see the data. Okay, so what we're going to do, so that's it. That's exactly what I wanted to do today. So what we're going to do tomorrow is not very much, actually, is to really look at how this framework develops. How can you use this framework to do statistics? And it's not that this kind of statistical inferential framework is found in many modern applications. So, for example, if you look at the kind of roots or of machine learning, which is basically, some of your computer scientists, most of the things which are done in, a lot of the things which are done in machine learning are basically using this Bayesian statistical framework. Okay, so if you know this, then essentially the things you will be doing in the future will at least be understood from core principles. So there's a point to this. It's just that you may not see it yet. Okay, so that's it. So we're going to look at 5 pages tomorrow, and if you're more interested in the actual course, next week is exam revision. Thanks very much for your attention.